Now, this is a very important topic about interrupt priority management. We have been talking about priority management even before, but this section deals with the interrupt priority management in a deeper fashion. So, all Cortex M processors, both the ARM version 6 and version 7 of the microcontroller variant, actually has interrupt priority management in it. So, whether and when an exception can be accepted by the processor and get its handler executed is dependent on the priority of the exception and the current priority of the processor. Uh, the current priority of the processor would mean whatever thread. So if the current currently the processor is executing, it's within an interrupt service routine which is higher than uh, the current interrupt that is being raised, then that particular interrupt will have to wait until the higher priority interrupt is serviced. Then you have a, as we said, as we discussed, a higher priority exception can preempt a lower priority exception, and this is called as a nested exception interrupt scenario. Now, this entire preemption mechanism is automated, in the sense in the entire preemption mechanism is taken care of by the Cortex M4 hardware. We don't have to worry about the interrupt nesting. Some of the exceptions, like reset, NMI, and hard fault, they have fixed priority levels. That is, except for these three interrupts, or except for these three exceptions, rest of the exceptions are configurable. That is, you can configure their priority. They are represented with negative numbers to indicate the same. That is, their exceptions are above 0. Now, don't confuse this priority number of 0 with the interrupt number of 0. These two are separate entities. And there are 256 programmable priority levels with a maximum of 128 levels of preemption. Now, we will see very soon in the next slide that there are not really 256 programmable priority levels. It is left to it depends on the particular Cortex variant as to how many programmable priority levels are being allowed or designed into the processor, because higher the number of priority levels, it actually increases the complexity of the processor design also. And of course, that is what is mentioned in the next point. The actual number of available programmable priority levels are decided by the silicon chip designers. Now, Cortex M4 STM32F411XC or XC, whatever we are going to work on, makes use of the nested vector interrupt controller and is able to manage 16 priority levels. Like I said, you have space for 256, but this handles 16 priority levels, and it can handle up to 62 maskable interrupt channels plus 16 interrupt lines of the Cortex M4. Now, continuing, to increase the priority control of the interrupts, we have something called as the priority grouping. Another feature of Cortex M4 exception priority management is that the priority is decided by the upper 4 bits or upper bits of the particular priority register. For example, if you want to set the priority of an interrupt, these bits are unused basically. So when if you have to set an interrupt priority to be, say, 4 has to be shifted to this particular higher 4 bits of the register. So you say 4, and then you have to rotate it by 4 places to actually come here. Okay, so say you declare the priority, and then you have to move it, do a left shift for it to appear here. Okay, so that is something that you have to remember. The priority to increase priority control, again, we have 4 fields here, and these 4 fields are again divided into groups of 2. Okay, so one is the upper field defines the group priority, and the lower field sub priority. So for example, you could have lower 2 fields as sub priority and upper 2 fields as group priority. So you could configure it that way. So in that way, you will only have 2 bits to decide group priority, and within that group you will have 2 bits to decide sub priority. And so that point can again move around, and you can have all 4 bits to have a bits in a group, so you do not have any sub priority there. You will have all 4, so there will be 16 levels of in group priority, and the priority of an interrupt is determined by the group priority, not by the sub priority. So if we are splitting up these 4 bits into 2 bits each, one for group and one for sub, or okay, so to better understand it, say we split it up into 3 and 1. So 3 bits for group priority and 1 bit for sub priority. So for 3 bits we can go up to 0 to 7. So say we can have 8, we can represent 8 priority levels. So this is what is going to be considered when the NVIC tries to discern between which interrupt to service next. Okay, so preemption and everything will be happening on these 3 bits, and this bit is the sub priority bit. Okay, so when the processor is executing an interrupt exception handler, another interrupt with the same group priority as the interrupt is being handled does not preempt the handler. Okay, so if you have the same group priority, it will not preempt the handler. Okay, so if multiple pending interrupts have the same group priority, the sub priority field determines the order in which they are processed. If multiple pending interrupts have the same group priority and sub priority, the interrupt with the lowest IRQ number is processed first. So here, if you have the same group priority and one interrupt has a lower sub priority, that is going to be serviced second. Okay, and the one with the higher sub priority is going to be accessed and serviced first. Now, if you have the same group priority and sub priority, as we said, it will be on the actual interrupt number, as we saw the numbering from say 0 to, we saw 0 to 85 in the case of our controller. So within that 0 to 85 range, whatever, say it is the interrupt number is actually 7, but it has the same group priority and sub priority, then if there is an interrupt, say interrupt number 6 that is being executed, 7 is going to be, if 7 is going to have to wait for 6 to complete to be executed. So this is the interrupt priority grouping scheme that we have in the case of our particular SOC. Now we saw the AI RCR register, okay, and there is a pri group field which we talked about previously. So there are different bit settings in the priority group field which we can do. As it says here, indicates the position of the binary point that splits the priority field in the interrupt priority registers into separate group priority and sub priority fields. So the table below shows that. For example, if you set 0xx, so 0xx would mean if the third bit, that the most significant third bit has a 0, this is a don't care. So whatever you set after that doesn't matter. Then the group priority bit is 7:4. Okay, 7:4 means in this setting. Okay, 7:4 in this setting means all the bits are group priority, no sub priority. So there are 16 priorities. Okay, so let me try to draw this and try to explain it so you understand it better. So suppose you have that register of 8 bits, and we are anyway using the first top 4 bits. So the bottom 4 bits are anyway not used, as you know, as we saw previously. So sorry about the bad drawing. So this is the register, okay, and we are anyway not using this part. This part is out of bounds. Okay, this part is out of bounds, as we saw. So when in the pry group, okay, in the pry group, so we saw this particular AIRCR register. Okay, so in the pry group field of the register, if you just set this, that is 0, all these 4 fields are considered as a group. Okay, so obviously the group priority will be 16 because all of them are considered. Setting this to 100, okay, has a split of 5 to 7. Okay, 5 to 7 would mean 5 is the out of 7. Okay, we will have 4 sub priority bits. Okay, so you will have 8 group priorities and 2 sub priorities. That is, it splits here. Okay, that is, the group priority will come here, and you can just have a choice of 0 and 1 for the sub priority. So 2 sub priority levels. Setting it as 101 in the pry group will actually have, it will split it into half exactly. So 2 group priority and two group priority bits and 2 sub priority bits. So 4. Making it 110 will make it, just this will only have 2, and sub priorities will increase to 8. So it comes here. Okay, so you have only 2, 0 and 1, and this entire thing goes into sub priority. And setting it to 111 will have, it's a complete, this entire, all the fields will be just sub priority. There will be no group priority. We will not be using that setting. In our case, for our use, we will use the group priority of 0xx, and we will use all the bits for our purpose. But then this is possible. I mean, you can actually set different group priorities and sub priorities, so that it depends on your use. Now let us try to understand how the interrupts behave under group priority and sub priority better. So let us say we have 3 interrupts. Say interrupt 1, interrupt 2, and interrupt 3. Now interrupt 1 is going to have its priority register, of course. Interrupt 2 again has it's somewhere. So interrupt 1 is, say, from the SCB, it is a system interrupt. Interrupt 2 is a peripheral interrupt. Interrupt 3 is an IO interrupt, whatever it is. But we are talking about configurable interrupts here. We are not talking about hard fault or PENDESV or NMI or anything of that sort. Okay, so these are the top 4 bits, not drawing the bottom 4 bits because they are not useful in our case. Our architecture doesn't permit that. So let's assume that we'll see 2 scenarios. One is a complete all 4 bits as a group, and then a 3:1 split. Okay, so let's say we have all 4 bits first. So if interrupt 1, so let us say that we set the priority of interrupt 1 to be 4. Okay, and since all the numbers here are all the bit fields here are considered within a group, 4 will be this 1, 0 and 0. This is 4. Say interrupt 2 has a priority of 3. Okay, so it is going to be 1, 1. So it is 0, 1, 0, 0, 0, 0, 1, 1. And interrupt 3 it has a priority of 1. So it is 0, 0, 0, 1. Okay. Now let's say that interrupt 1 is executing in the current time. So say interrupt 1 is executing in the current time. So, and then at that time interrupt 2 is asserted. Now, since interrupt 2 is asserted and interrupt 2 has a priority of 3 and this has a priority of 4, so interrupt 1 is halted and it is preempted by interrupt 2. So 1 is halted, it is preempted by interrupt 2, and interrupt 2 starts executing. Say at that time interrupt 3 comes in and interrupt 3 has a priority of 1. So obviously that interrupt is going to again preempt interrupt 2 because that has the highest priority. So what happens is, again interrupt 3 starts executing and we have interrupt 3 running. Once interrupt 3 completes, interrupt 2 completes, and then interrupt 1 completes. So this is how the preemption happens. So 2 is preempted by 1, 3 is preempted by 2, and then it goes back up in the reverse order. This is for the priority grouping of with all 4 bits. Now let us try to see if we split it up as 3:1, keeping the bits the same, how it looks. Okay, say we keep the bits the same, but then we separate out the higher. So what we do is, now we have made the top 3 bits as a group and 1 bit as a sub priority field. It could be anywhere. We are just seeing this scenario. So if we only consider the top 3 bits as a group, so what are the priorities now? The group priorities. Here the priority is 1, 0, that is the priority is 2. Here the priority is 1 and here the priority is 0, with a sub priority of 1, 1 and 0. Again, we see that the same thing is going to happen now, because 1 again has a priority of 2. This becomes 1 because we have split up this field now. So this is a sub priority field. So this is a sub priority field. So this will not be considered within the group anymore. So the group priority now becomes 2. The group priority, because we have a split. If we split it here like previous, then the group priority is going to become 4. Okay, so this is how the calculation is done. So now the group priority is based on this. Funny things can happen if your priority bits are different when you change the group priority and sub priority, but then this is how it is. But the behavior is going to be again this, because though the grouping changes, still interrupt 3 has the highest priority number. So this is how group priority and sub priority is decided in ARM Cortex M4. So we will see an instance. Of course, we will see preemption between SysTick and external interrupts 1, and this will be demonstrated in code. Now let's say that, let's take the same 3 interrupts, but in this case we have, if we take all the 4 bits as a group priority, this has a priority of 2, this has a priority of 3, and this has a priority of 1. Now let's split up the fields and make 3 bits as one group and the sub priority as 1 bit here. Okay, so now how does these interrupts look? So let's say that interrupt 1 is executing here. Okay, and interrupt 2 comes in at that point. Okay, interrupt 2 comes in at that point. However, interrupt 2's sub priority, so if you take the group priority, both have the same priority. Okay, interrupt 2 has a higher priority, higher in the sense it has a higher number, so means it has a lower priority. So this means that interrupt 2 is going to be suspended. It is not, so interrupt 1 will keep executing until interrupt 1 completes executing. 2 will not start. So this has to complete and then 2 will start, because the sub priority is, it has a lower priority than the interrupt here. Okay, Interrupt 3, of course, it has a higher priority because it is 0. But then this is the logic of how sub-priority works. So these two, if you see the group priority, both have the priority of 1. So which interrupt executes first is decided upon the sub-priority field. Okay, so this is how sub-priority works. Now if in case you had both these interrupts with the same set of bits, then the Cortex M4 will refer the interrupt vector table, and it will check for the IRQ numbers. So whichever has a lower IRQ number is going to be executed first.